So, hello everyone. I am currently a second year undergrad student from Willows Institute of Technology, and my name is Aditya Pratap, and I'm going to teach you limitations of scalar pipeline architecture. So, what is scalar pipeline? A scalar pipeline is typically a processor pipeline that produces one instruction at a time through a series of stages. Like, you can only execute one instruction at a clock cycle. And it's called scalar because it handles scalar data, that is, individual elements, not vectors or batches. So that's about scalar pipeline. So the major steps that undergo through scalar pipeline are fetch, decode, execute, memory access, and write back. Fetch. When we get the instruction from the memory, it's called fetch. Decode. Decode means to understand the instruction, does then execute the instruction that is understood by the memory. Then we access the memory from where we actually load or store the data. And we also write back to the memory, that is write operation. Why do we prefer scalar pipeline? Because scalar pipelines are easy to design and implement, and it's more preferred because of its simplicity. It is efficient, it is reasonable when like when it comes to light processors, and it is good for simple CPUs, for example, RISC-V processors. Now, what are the limitations of scalar pipeline? There are ample of limitations. For example, single instruction per cycle. No matter how efficient the pipeline is, the maximum throughput is one instruction per cycle. Only a single instruction can be fetched and executed in one cycle. In other high performance systems, this limit performance as multiple instructions often could be executed in parallel, but are. Suppose if you want to execute one or more than one instruction in parallel, then you can't do with this scalar pipelining method. For that, you need to prefer any other method. In scalar pipelining, only one instruction can be executed at a go. Now, the second limitation is structural hazard. Structural hazard often occurs when the hardware of the structure, the hardware of the pipelining method, is uh, not able to take the load of the request which is fetched. For example, in scalar processors typically share resources like single ALU, single memory unit, and single register file. This leads to pipeline stalls when two stages conflict over a resource. This is called deadlock condition in OS. If we compare this with OS, it is deadlock condition. It increases latency and reduces efficiency. Of course, like there will be a jitter, there will be a redundancy as well, especially in resource constrained CPUs like embedded systems. Now, data and control hazards. Data hazards arise when instruction dependent on the result of a previous instruction still in the pipeline. Like the instruction which we want to uh, execute, it is dependent on the instruction of the previous instruction which was executed out of the pipeline. It can be of three types: raw, which is read after write; war, write after read; and war, that is write after write. In this instruction, the first one, you can see there is written like add R1, R2, and R3. That means we have to add R2 and R3 and fetch the result in R1. And in the second clock cycle, it is asked to subtract R1 and R5 and fetch the result in R4. Here, the execution of second step is dependent on the first step. If R1 and R2 are added and the result is fetched in R1. Then only second step will be executed. And raw hazard occurs when, due to any related issue, R1 is not loaded correctly. Now, let's come to war result. In war result, we have to, this is right after read. Like, we are reading a data and we have to write after. In this example, the clock cycle 1 asks us to subtract R1 minus R2 and fetch the result in R2. And in second instruction, we have to write R3 plus R4 in R1. Here, we are reading R1. And after reading R1, we have to take that register in use and fetch the result of R3 plus R4 in R1. Hence, this occurs in, this also creates a problem if there is a issue in executing the first instruction. And in third third type of problem, if two instructions write before the instruction when the final value of R1 will be incorrect. For example, there are two instructions. We have to write the we have to write the result of both the instructions in R1. If R2 writes before R1, then sorry, if instruction 2 writes before instruction 1, then there will be a wow result. There's one more problem associated with it, that is control hazard. Occurs when the processor encounters a branch instruction and does not know which instruction to fetch next. Like, until the branch is resolved, the pipeline might fetch the wrong instruction. For example, in this situation, it was R2. If R1 is equal to R2, then we have to go to level. What if Beck is true? This ad should not run. Matlab, if Beck is true, then this ad should not run. Hence, this creates an hazard, which is like creates a confusion by the architecture to choose or not choose the uh, given lines of statement. And scalar pipelines might not support prediction. This leads to flushes and pipeline bubbles, reducing efficiency. Pipeline bubbles are also called stalls. Now, what are the impact? What does it? How does it impact in instruction level parallelism? Number one is sequential execution restriction. Scalar pipelines fetch and issue only one instruction per cycle, and this limits parallelism because even if multiple instructions are independent, they can't be issued or executed simultaneously. You can't do it simultaneously. You can't fetch two records at a time, and only one instruction flows to each state at a time, reducing IL. Now, second is data hazards prevent parallel execution. Even independent looking instructions may have data dependencies, creating delays or stops. The CPU must wait for prior instructions to complete before moving on. Like we have to do priority scheduling. Now, pipeline stalls and bubbles. Pipeline stalls are inserted when hazards prevent next instructions from safely executing. These empty cycles reduce pipeline's throughput and overall efficiency. Now, how superscalar pipelines can help us to uh, and to overcome the limitations produced by scalar pipeline. In superscalar pipeline, we can fetch, decode, dispatch, and execute multiple instructions simultaneously. It will increase the throughput potentially by 2x or 4x times than scalar for suitable instructions. Hardware to handle data hazard provides hardware to handle data hazards. Like superscalar architecture improves performance by executing multiple instructions per cycle using parallel functional units and advanced hazard handling. It supports out-of-order execution, register renaming, and branch prediction to maximize instruction level programming. These are few techniques which is used by super scalar pipeline hardware to increase the efficiency. Now, dynamic instruction scheduling. Super scalar processors often execute instructions out of order if dependencies allow. For example, where we have to load something from the memory and depends on R1 if it waits or executes the other statement. Now, branch prediction, speculative execution. Superscalar processors use branch prediction to test outcomes of branches early. They also use speculative execution to continue executing down the predicted path. Like it also has the capability of predicting the output of the branch, and it also continues executing the predicted path by speculative execution. Thank you for listening, being with the video. We'll come with more content. Thank you.